A single calculation should never be able to silence a nation. But there was a moment when numbers on paper made powerful people in the United States go quiet, not because they were wrong, but because they were too right. And the man behind it was not a general, not a politician. It was a scientist who once spoke about stars and suddenly found himself calculating the end of worlds. Carl Sagan did not begin his career thinking about nuclear weapons. He studied planets, atmospheres, the chemistry of distant skies. He looked upward, always upward, as if the universe itself was the final answer. But in the Cold War years, something changed. The sky stopped being distant and started becoming fragile. There is a strange idea in science that understanding something deeply enough can make it more dangerous, not less. And Sagan began to ask a question almost no one wanted to hear out loud. What happens if we stop treating nuclear war as politics and start treating it as physics? Not morality, not ideology, just consequence, cold mathematical consequence. And this is where everything begins to shift, because Sagan and other scientists started building models, not of cities, not of nations, but of the atmosphere itself. And what they found was unsettling in a way no one expected. They realized that nuclear weapons were not just explosions on the ground. They were events that could reach the sky, and the sky, once disturbed enough, could change everything beneath it. But here's where it gets strange. Even before the explosions were fully understood, the mathematics already suggested something darker, that the danger was not only in the blast. It was in what the blast would erase above us. And this is where another mind enters the story. Roger Penrose was thinking about reality in a different way. While Sagan studied atmosphere and consequence, Penrose explored geometry, infinity, and the hidden structure of the universe itself. Different paths, different questions, but both circling something deeper than war. They were asking what happens when systems become extreme, when scale breaks intuition, when human imagination fails, but physics does not. And nuclear war is exactly that kind of system, because at a certain point numbers stop feeling real. Millions of degrees, thousands of detonations, atmospheres turning opaque with heat and debris. But humans cannot feel those numbers, so the mind ignores them, and that is where danger begins, because reality does not ignore them back. Scientists started running simulations, not simple ones, global ones, and what emerged was not just destruction in isolated cities, but something spreading outward, a chain reaction through the air itself. But that is only half the story. Because buried inside those early models was a question so uncomfortable that even the scientists struggled to phrase it correctly. What if nuclear war does not end when the bombs stop? What if it continues in the sky? At first the idea sounded almost impossible. The atmosphere is vast, it is resilient, it has survived asteroid impacts, volcanic eruptions, ice ages. But nuclear war is not a single strike. It is many fires, many cities burning at once. And fire, when scaled beyond imagination, behaves differently. Smoke rises, not just smoke, but soot. Dark particles reaching high into the atmosphere. And then something unexpected happens. The sun begins to fade, not disappear, but weaken. A global dimming, a cooling, a slow transformation of the planet's surface conditions. But scientists found something even more disturbing. The models were not linear. They escalated. Small changes in assumptions produced massive changes in outcome. And that is where Sagan's calculations became controversial, because they suggested a possibility no government was prepared to consider seriously. That nuclear war might not just destroy cities. It might disrupt agriculture. It might collapse climate systems. It might change the rhythm of life on Earth itself. But why did this cause silence in political circles? Why would numbers create discomfort instead of debate? And this is where the story takes a darker turn. Because Sagan was not just calculating destruction, he was mapping feedback loops, systems that amplify themselves. Fire creates smoke. Smoke blocks sunlight. Less sunlight cools the surface. Cooling changes atmospheric circulation, which traps more smoke. A loop, a spiral, a system that does not need permission to continue. And once the mathematics revealed that structure, something shifted in the conversation around nuclear strategy. Because suddenly the question was no longer who wins. It was what remains, and that question had no comfortable answer. But here's where everything changes again. Some scientists refused to accept the early conclusions. They argued the models were too uncertain, too extreme, too dependent on assumptions about burning cities and atmospheric behavior. And in the middle of this scientific tension, a deeper philosophical question emerged. How much evidence does it take before imagination becomes responsibility? Because the numbers were not fiction, they were extrapolations of known physics, fire, atmosphere, radiation, light. But the scale was beyond lived human experience. And that is where minds like Penrose became strangely relevant, because Penrose often explored how systems behave when pushed to extremes, when intuition fails and mathematics takes over. What happens when reality is governed by equations that feel unreal? Do we trust experience, or do we trust calculation? And Sagan, standing in the middle of this intellectual storm, began to articulate something quietly radical. That survival might depend not on predicting war perfectly, but on respecting what imperfect predictions consistently point toward. And that idea did not sit comfortably in any institution, because it implied something unsettling. That uncertainty does not equal safety, and absence of proof is not proof of absence. But there is a final layer to this story that almost no one discusses openly, because behind the physics, behind the models, behind the scientific debates, there was a human realization forming slowly. That civilization had reached a point where it could simulate its own extinction, not through prophecy, but through computation. And once that becomes possible, a new kind of responsibility emerges. One that is not scientific, not political, but existential. And this is where Sagan's work begins to take on an almost philosophical weight, because he was not just asking what nuclear war would do. He was asking what it means to know what nuclear war would do, and still move forward anyway. But just as the models became clearer, and the implications sharper, something unexpected happened inside the scientific community. A growing discomfort, a hesitation, as if the mathematics itself was pointing toward a conclusion too large to fully accept. And then came the moment that changed everything, when one of the early global climate simulation results suggested a scenario so extreme that even its creators paused before publishing it, not because it was wrong, but because it was too coherent, too internally consistent, too difficult to dismiss. And right at the edge of that conclusion, the story was stopped, not by lack of data, but by the realization that continuing forward would force a question no one was ready to answer yet, a question about whether knowledge itself carries a threshold, beyond which understanding becomes irreversible. And that is where we will stop for now. Because what those early models truly suggested goes even further than what Sagan initially revealed. The silence after those early findings did not last. It never does. Because once an idea exists, it does not stay contained inside laboratories. It spreads, quietly at first, then all at once. And soon what began as speculative modeling inside academic circles started reaching places it was never meant to reach. Government offices, military briefings, closed-door rooms where the air always feels slightly heavier than normal. And in those rooms the question was no longer whether the calculations were interesting. The question was whether they were dangerous, because the work associated with Carl Sagan and his collaborators had begun to crystallize into something more formal, a framework, a hypothesis, a warning written in the language of physics. And it would later be associated with what became known as nuclear winter theory. But at the time it did not have a dramatic name. It was just numbers. And those numbers suggested something that made even seasoned analysts pause. That after a large-scale nuclear exchange, the atmosphere might not recover quickly. It might change state, not metaphorically, literally. The surface of the Earth could cool dramatically. Light could be reduced for weeks or months. Agricultural systems could collapse not from blast damage, but from absence of sunlight. And this is where everything becomes more unsettling, because the models did not rely on imagination. They relied on combustion physics, atmospheric circulation, basic radiative transfer, things already known, already verified, but now assembled at a planetary scale. And scale changes meaning. But here's where it gets strange. The more refined the models became, the less room there was for comforting uncertainty. Instead of scattering wildly, the results began to converge. Different teams, different assumptions, similar outcomes, a pattern emerging from independent approaches. And that is when the conversation stopped being purely scientific. Because if multiple models point in the same direction, then disagreement becomes harder to justify. But acceptance becomes harder too. And somewhere in this tension, something important happened. The work was presented in policy contexts. Briefings were held, summaries were written for decision makers who were not physicists. And in those rooms, something unusual was reported. Not disagreement, not refutation, but silence. A kind of institutional stillness. Because the implication was not just that nuclear war would be destructive. That was already known. The implication was that it could be self-altering, that it might reshape the conditions for survival itself. And that raises a bigger question. What does deterrence mean if the aftermath is not survivable in any familiar sense? But there is another layer that rarely enters public discussion. Because while Sagan and others were refining these models, thinkers like Roger Penrose were exploring something different but strangely connected. Not war, not climate, but the limits of understanding itself. Penrose often dealt with systems where intuition fails but mathematics continues, where reality does not bend to human expectation. And nuclear winter models in their own way became exactly that kind of system. A place where intuition says this cannot scale further, but equations say it already has. And this creates a kind of cognitive fracture, because humans are not built to emotionally process planetary scale feedback loops. We understand fire in a house, not fire in a hemisphere. We understand smoke in a room, not smoke in a stratosphere. But the physics does not care what we are built to understand. It only continues. And this is where the story takes its most uncomfortable turn, because as the models grew more widely discussed, critics emerged. Some argued that soot production estimates were too high. Others said atmospheric dynamics were too uncertain. There were debates over cloud formation, over particle lifetimes, over sunlight absorption rates. And scientifically, these were valid discussions, but underneath them, something deeper was happening. A struggle over what kind of knowledge is acceptable when consequences are extreme. Because if the worst-case scenario is too large to imagine, does it become easier to dismiss, or harder? And in the middle of this uncertainty, Sagan made a choice that would define his public legacy. He stepped beyond purely academic communication. He spoke in broader language. He tried to translate equations into consequences, not to exaggerate, but to make scale emotionally accessible. And that is where the resistance intensified. Because once science enters public imagination, it stops being just science. It becomes narrative, and narratives can be accepted or rejected. But here's where everything changes again. Even as debate continued, something unexpected happened in the scientific record. Newer simulations began refining earlier predictions, not weakening them in every case, but sharpening them in specific ways, showing that under certain scenarios, the cooling effect could be rapid, very rapid, and potentially global in reach. Not uniform destruction, but systemic disruption. Agriculture systems failing in different hemispheres at different times. Food chains destabilizing, not from a single cause, but from cascading deficits. And this is where the phrase feedback loop becomes more than technical language. It becomes existential. Because once a planetary system enters feedback behavior, control becomes complicated. Not impossible, but delayed. And delay matters. Because even small delays in response to global scale events can amplify outcomes dramatically. And this is the uncomfortable mathematical truth that emerged. That the danger was not only in the initial event, it was in the reaction time of the planet's systems. But there is one final detail that ties this entire intellectual history together in a way few people notice. Sagan was not trying to predict the exact future. He was trying to map boundaries, limits, edges of possibility. And Penrose, in his own domain, often did something similar with the structure of reality itself. Both were in different ways asking, where does intuition stop working? And what exists beyond that point? Because nuclear weapons forced science into a rare position, where abstraction was no longer safe to keep abstract, where thought experiments had physical consequences, and where calculation became a form of responsibility. And now we arrive at the moment the story has been moving toward all along. A moment not of conclusion, but of confrontation. Because if the early nuclear winter models were even partially correct, then the meaning of nuclear deterrence is not just strategic, it is planetary. And that realization leads to a final, unsettling question, one that was never fully resolved in those early briefings. If a system is capable of ending not just cities, but the conditions that sustain cities, then what exactly is being deterred? And more importantly, what happens when someone believes the system can still be controlled anyway? That question was left hanging in the air of those rooms, unanswered. And still, even now, it has not fully gone away.